That'd be great. Thanks very much. So this lecture, we're going to look at single degree of freedom systems. So I mentioned some of the basic stuff last time about vibrations, and I mentioned that we had this concept of degrees of freedom, and that this course was going to focus on single degrees of freedom. So we're going to do some notes about that. And the shorthand, of course, for degrees of freedom is DOF. So we tend to write things like this, SDOF. Okay, so SDOF means single degree of freedom systems. Okay, so that's the kind of shorthand that we're going to use for that. And as I said last time, I'm going to go through these notes, writing them down to explain what happens, but you can obviously follow the lecture slides if you want that are on MOL, and annotate those if you prefer. Okay, so whichever you prefer. So what is a single degree of freedom system? Well, the most common one that you're going to find consists of a mass, which we call M, and a spring, which we're going to call K. So there's several different ways that single degree of freedom systems can be represented, but that's a very common way. And what we tend to define is that the motion of the mass is defined in this direction by x. Okay, so this thing can move up and down vertically. Okay, now the way I've drawn it, of course, if you actually really had a mass standing on a spring, it could move from side to, it could rock from side to side, and it could twist this way, couldn't it? They would all be different degrees of freedom. But we're going to make the assumption that it can only move up and down in one direction, and that's the 1 degree of freedom, or the single degree of freedom. Okay, so when we put x on the diagram, what we're showing is that there's just one way in this that this thing can move, which is up and down. Quite often we'll put a brackets t, okay, next to the x, and that indicates that x varies with time. Okay, so it's a dynamic problem, so x is a function of time, or it varies with time. Okay? So the equation of motion comes from F equals ma, which is what we talked about last time, isn't it? Which is Newton's second law. Okay, so F equals ma. We're going to do two different parts to it. Okay, so we're going to first we're going to look at the static equilibrium, and then we're going to look at the dynamic equilibrium. Okay, so the first thing to look at is static equilibrium. And what that means is that if we place this mass on top of the spring, before any vibrations happen, the spring is just going to go down due to the effect of gravity, isn't it, essentially? So if I just move this over slightly so we can see the diagram. So there's some initial position. Sorry, I'll just move this over so we can see. So there's some initial zero position here, and when we put the mass on top of the spring, it goes down just because of gravity. Okay, it just pushes the spring down because of gravity. And that little bit of movement there we're going to call x subscript s, okay, which is x static. Okay, so that's the amount that it moves down just due to the mass being put on top of it. And if we do the Newton's second law, what we find is that the spring stiffness constant K times that amount of x static balances with the mass times gravity. Okay, because that's what that static equilibrium is telling us. In fact, for most of the time, let me just move back so you can see that what I've written down. Okay, so I've written down that the static equilibrium, the spring constant K times the xs equals m times g. Mass times gravity. Because we're interested in the vibrations, we tend to, most of the time, we tend to assume that this step has been done. Okay? And so, on the little diagram where I've put the x on the right-hand side, you can see that I've kind of positioned this in the middle of the mass, which indicates that I'm assuming that the static equilibrium has already been taken account of. And so now the x of t is just the dynamic displacement. Okay? So if we consider the dynamic equilibrium, what we find for this case is we have mx double dot equals minus k times x. Okay? So now the acceleration is x double dot. That's because we're interested in the acceleration, the dynamic movement of the mass. Okay? So that's represented by x now. Okay? So we get x double dot in Newton's second law instead of where we had g as the gravity force last time. Okay? And what this is telling us is that the inertia force, okay, is acting in one direction, and the restoring force is trying to bring the mass back to, trying to restore it to its original position. Okay? And usually what we do is we shift this to the same side so that we have an equation which reads like this: mx double dot plus kx equals 0. Okay? So this is a mass and a spring system, and this is the kind of fundamental equation for that system. Okay, so this there's a couple of other ways of deriving that, particularly using free body diagrams. Okay, and what I'll do is, as we go through the course, I'll show you those methods as well. And in the tutorial sheets, there's a chance to practice drawing free body diagrams. Okay, so we'll talk through other ways of getting to this equation as we go through the course. But for now, we can just, if we just take this as the equation that governs the vibrations or the oscillations of this mass spring system, okay, what we're going to do is we're going to try and substitute or guess a solution, and then see if we can work out if we can solve this equation, this second order differential equation in terms of x, isn't it? Okay, so we're going to try and solve this equation now. So we're going to assume a trial solution. And our trial solution is going to be x equals a constant c times e to the s t. Okay, so c is a constant. So if you remember from last lecture, I said that we could assume that says c is a constant, all right? So last time I said that we could assume that we could represent sine waves as exponential terms, didn't we? Okay, so what you'll see is that I'm assuming that x is some arbitrary constant times an exponential, and what will come out is that will be some sine waves, essentially, okay? But we start by assuming, in fact, we could start by assuming sine waves, okay? So again, there's multiple ways of solving this, but I'm going to take you through this method, okay, which gets to the same kind of result. So, if we have x equal to this, then x double dot is equal to s squared c e to the st, isn't it? Okay? So if we just differentiate the exponential function with respect to time twice, we get an s squared at the front. So then we can make the substitution in this equation. We can substitute for x double dot and substitute for x, okay, and see where that leads us. So what we get is mc s squared e to the st plus kc e to the st equals 0. Okay, so that's just substituting that in, and of course we've got some common terms here, so we can rewrite this as the constant, and then inside a bracket we have ms squared plus k, and then outside the other side we have the e to the st, and that all equals 0. Okay, that's sometimes called the auxiliary equation. And what people normally do at this stage is that they divide out by the exponential term. Okay, so we've got an equation which is equal to 0, so we can divide through if we want to. So this is equivalent to saying that essentially c ms squared plus k equals 0. So the time-independent part essentially is this. So you can see with this equation, to satisfy this equation, we've got two choices. Okay, so either the constant c is 0, or the bracket 0. Okay. Now, if the constant is 0, okay, that goes back to, if we go back to our assumed solution, if the constant is 0, then it means x is 0, and that's a valid solution, but it means that there's no motion. Okay, so that's like the static. Okay, so it's fine, it works, but it's not a solution of interest to us. So the solution of interest to us is when the bracket is 0. Okay, so when this bracket is 0, sometimes called the non-trivial solution. Got too many batteries here. So let's just say either c equals 0, which is trivial solution, or c not equal to 0, and ms squared plus k equals 0, non-trivial. So, if we've got this situation where we've got ms squared plus k equals 0, okay, that's a quadratic, isn't it, that we've got to solve? Okay, so we've got to solve this quadratic. So we just use the standard formula for solving a quadratic, where the roots s1 and 2 are equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's the usual solution for solving quadratic, isn't it? Now, in our quadratic equation, what have we got? We've got the a parameter is equal to the mass m. The b is 0. Okay, so we've got no coefficient multiplied by just s on its own, so b 0. And the c coefficient, the small c, is equal to the stiffness constant for the spring, k. Okay, so they're the three things that we've got to plug into this equation. So what we get is that s1 and 2 is So we plug those in. It's equal to plus or minus the square root of minus 4mk all divided by 2m. And so we can simplify that. So the first thing we can do is we can notice that the 2's will cancel out, won't they? Because this is essentially 2 squared inside this square root here. So we can bring that outside the square root, and then that cancels with the 2 on the bottom. Okay, so this is equal to plus or minus square root of minus mk over m. Okay? And now if I take a square root of m outside and I divide this m into square root times square root, I can cancel the square root of m on the top and the bottom. Okay, so I can write this is equal to plus or minus square root of minus k over m. And then finally what I can do is square root of minus 1 is j, of course. So of course this finally just equals plus or minus j times the square root of k over m. Okay? Now this square root of k over m is an important parameter. Okay? And what we do is we're going to let the square root of k over m equal omega subscript n, okay, which is the natural frequency. Okay, so if you remember from last lecture, I introduced this idea of omega as a frequency, and I said that there were several different variants of that, and so this is one of the important ones. So if it's got a subscript n, it means the natural frequency, and it's the square root of k over m. Okay? Sometimes, because in this system we're not assuming that there's any energy loss or damping, sometimes also called the undamped natural frequency. Okay? So sometimes also called the undamped natural frequency. Oops, sorry. It's hard to get this. Alright, there we go. So, the roots S1 and 2 are equal to plus or minus j omega n. Okay, because square root of k over m is now defined as omega n. And as I'm sure you'll all remember from your courses on differential equations, if you solve a differential equation and assume a solution, so if you assume that x is equal to a constant times an exponential, then you find the roots s, so we found the roots omega n. Okay, so you can just add solutions together. Okay, so in fact what we're going to do is this is going to be constant 1 times e to the j plus omega nt, and we can add a second solution because we've got two roots, so effectively we've got two solutions. This is e to the minus j omega n times t. Okay, so this is our solution to the differential equation, but it's still not in the form of sine waves, and of course we'd like to. It's intuitive for us to represent it as oscillations as sine waves. So that's what we're going to do. So we're now going to use the fact that e to the plus or minus j omega nt is actually equal to cos omega n times t plus or minus j sine omega n times t. So if we make that substitution into the previous equation. So if we substitute these two expressions, the plus and minus expressions, into here and here, what we get is that x brackets t is equal to c1 plus c2 cos omega n times t plus j c1 minus c2 sine omega nt. Okay, it's just fallen off the end slightly. Now these C1, these big constants, C1 and C2, they're just arbitrary things. Okay, so I can redefine them as I want because we don't know what they are at the moment. We're going to work out what they are in a minute. So we're going to write this as x of t equals a, which is a new arbitrary constant, okay, which is just c1 plus c2 cos omega nt plus b sine omega nt. So a and b are just are new definitions of the arbitrary constants, just simplified into two new labels, okay? If I differentiate this, I get x dot of t equals minus omega na sine omega n times t plus omega nb cos omega n times t. So now I have displacement and velocity for this single degree of freedom system. And so we can work out what these arbitrary constants are by looking at the case when time is equal to 0. Okay? So when t equals 0, then we write it like this. So x brackets of 0, okay? So you can see that when we write the x of t, okay, so when we write the x of t here, this is any time, okay, some arbitrary time, but of course if we set time equal to 0, we tend to write this as x brackets 0 to indicate that that's a special case when the time is 0. Of course the sines and coses have very specific values if the time is 0, because in the brackets of the sine and the cos, these are going to make sine 0, aren't they, because you're going to have 0, sine of 0 effectively is 0, and cos of 0 is 1. Okay, so you're going to get some special things happening, cancelling out. And what happens is, you just get, for x, you get, at time 0, you just get a, because you've got a times cos of 0, which is 1, and the sine term disappears. Okay? And then the x dot at time 0 equals omega n times b. Okay, same logic. The sine term disappears. The cos goes to 1. Okay, so we're just left with this. Okay. So finally, you can write that your solution to this differential equation is equal to x0 times cos omega nt plus x dot 0 over omega n sine omega n times t. Okay? So that expression defines how the system moves, you know, what types of oscillation we have. Okay? And you can see that it's based on it needs the initial conditions, right? The x of 0 is the initial displacement, and the x dot of 0 is the initial velocity. Yeah. I've incorporated the J into the constant B. Okay, so when I redefine my constants, I've put it in there. So what we'll see as we do the course, we'll see how this can be simplified, how it can be used in various ways. But to give you a flavour, I'm going to do a quick example. Okay, and this example is in the PDFs of the lecture notes. Okay. Let's see if we can make space for it here. Okay, so example. So if we've got a system like this, spring, mass, okay, and K is equal to 9.87 meganewtons per meter, mass is equal to 2,500 kilograms, X, I think I've drawn this too big now, haven't I? Have I drawn it too big? There we go, we can just about see that, can't we? Does it make any difference if it's hanging down or if it's like the other way I drew it, right? The spring was underneath. Does it make any difference? Doesn't make any difference, does it? So essentially, once the static part's been taken account of, any oscillation is essentially going to be equivalent whether the spring is like pulling from above or from underneath. Okay, so you don't need to worry about that. So in this example it says mass pulled down 0.02 meters, okay, and it says asks you to find static displacement. It asks you to find a couple of other things, but what we'll do is natural frequency. What else? Maximum acceleration. Okay, so this is a kind of question you might get in a tutorial sheet or possibly part of an exam. You get given some parameters. You say you've got a single degree of freedom system, okay, with a mass and a spring. Find what these different things are. Okay, so we'll have a go at that. So let's try and do the static displacement. So that comes from the static equilibrium equation that we wrote down, doesn't it? So if you remember, we wrote down this equation that the stiffness of the spring times xs, which is the static displacement, was equal to mg, wasn't it? Okay, so we can say that xs is equal to mg over k, can't we? Okay, so we just plug in some numbers for that now. So xs is equal to 2,500 times 9.81 divided by 9.87 times 10 to the 6. So who's got a calculator? What's the answer? Ha 2.5 millimeters, yeah, exactly right. So I think it comes out something like 2.48 times 10 to the minus 3 meters, which you can write as 2.5 millimeters. And like all engineering problems, you know, because you're engineers at the end of the day, aren't you? If you said to yourself, does that seem reasonable? Okay, it seems like a reasonable number, doesn't it? Okay, quite a big mass, 2,500 kilograms is quite big, but the spring stiffness is pretty significant, isn't it? Okay, big spring stiffness, So 2.5 millimeters sounds like a reasonable number for a static displacement. If it was 2.5 kilometers, you'd be thinking, I've got something wrong in my math somewhere. There's some things gone wrong. Okay, but it's not. So we're okay. So next thing we're going to look at is the natural frequency. Okay, and we've just defined that to be omega n, which is equal to the square root of k over m. Okay, so that's what we said it was. So here we'll write omega n is equal to square root of 9.87 times 10 to the minus 6, sorry, 10 to the 6, over 2,500. And that equals what? Who's fastest with the calculator? Very good. 62.8, but what's the units? Very good, yeah, radians per second. So it's worth just pausing for a minute to think about these units. So this omega thing that we introduced, sometimes called the circular frequency, okay? Because, and the units are radians per second. Okay, so the clue of circular frequency sometimes helps you to remember that that's the units. Okay, so if we have a time period t for a sine wave, okay, so if we have a time period t like that, the frequency in hertz is usually written as f, and that's 1 over t, isn't it? Okay, so that's in the units of hertz. Yeah, you've seen that before? Okay, so 1 over t gives you the frequency, which is normally a curly f, and that's hertz. And to get to omega type frequencies, whatever it is, you times by 2 pi. Okay, and then that's in radians per second. So you have to be careful, because sometimes frequencies are given in hertz, sometimes they're given in radians per second, okay? But we nearly always differentiate that the circular frequencies, or the radians per seconds, will be some type of omega. So it'll either be omega n, or it'll be another. We use some different omega expressions, okay? So it'll be one of the types of omega. Okay, so the next thing we're going to look at is maximum acceleration, okay, and to get so up until now we haven't had to use our equation of motion, have we? Okay, to answer this question we haven't had to use the equation of motion, so now we have to use the equation of motion. Okay, so if we just go back and have a quick look, so we've got this equation of motion here. Okay, so this is our equation of motion. We're now going to use this to work out the maximum acceleration. And the key thing to notice is these terms here, okay? So these terms here, because often they are given to you in the question, okay? In this question it says the mass is pulled down 0.2 meters and then it's released, okay? Then there's an oscillation, okay? What it means is you pull the mass down to 0.02 meters, okay? At that point there's zero velocity. Okay, it doesn't say there's zero velocity, but it implies it. Okay, so it means that x dot 0 is x dot with brackets of 0 is equal to 0. Okay, so that's equal to 0, and this is our 0.02 meters. Okay, that's the initial displacement. It's been pulled down, then we release it. Okay, and then we get some behavior afterwards. Okay. So because this initial velocity is set to 0, the equation is actually simplifies, doesn't it? So it simplifies to just a cos term. Okay? And if you think about it, that kind of makes sense, doesn't it? Because if we start something off that's going to oscillate, like a cos wave, and this is 0.02, our initial condition here, okay, that kind of seems logical, doesn't it? It's just going to oscillate like a cosine wave, starting from a value that we've stretched the spring to a value, we let it go, and it's just going to oscillate and stay in that cosine wave the whole time. Okay, so there's a kind of logic to that. But the question is actually asking us for maximum acceleration, so let's just go back to where we were. So if we have this simplified expression that x is equal to x0, the initial displacement, times cos omega t, omega nt, then it means that x double dot, the acceleration, is equal to minus omega n squared x naught cos omega t, isn't it? Sorry, omega nt in the brackets. Okay, so that's the acceleration solution, isn't it? And where does the maximum occur? Well, in terms of the right-hand side, how do we make the right-hand side a maximum? Okay, because the cosine is varying with time. Okay, so the maximum cosine value is 1, isn't it? Okay, so to get a maximum value on the right-hand side, we have to take cos equal to 1. Okay, so what we actually get is that x double dot max is equal to minus omega n squared x0. Okay, and we know what both of these things are, okay, because we've just worked them out. So this is equal to 62.8 rads per second, and then we square that, and then this thing is what is given to us in the question. It's 0.02 meters. Okay, so what do we get if we do the numbers on that? What's the answer to that one? Very good. Yeah, minus 78.8. And what are the units? Very good. Yeah, meters per second squared, because it's an acceleration, isn't it? Okay.